Right, good morning. Today we're going to talk about the triangular wave oscillator. All right, what circuit is this? It's already known to you. What type of circuit is that? It's an integrator, all right. It's an integrator circuit. Now, if we put a positive input there, it will basically integrate negative. If we switch it to negative voltage, it will integrate positive. Not very practical because you must go and play around with the switch, all right? But that's just to explain how to get that triangular wave output by using an integrator. All right, that brings us to the practical triangular wave oscillator. All right, in this case, we got a comparator. Now we know the output of the comparator will always go to positive maximum and negative maximum. What will determine those maximum values? It will be determined by the supply on the comparator, all right? Now, if my output is negative maximum, what will happen? It will integrate positive. When my output of the comparator is positive maximum, it will integrate negative. All right. Now we just use the comparator to basically get a square wave, and then we will convert that to a triangular wave. All right. You with me? Yes. Any questions? We can also look at the trigger points. Right, the upper trigger point will be basically the maximum positive value, R3 divided times R3 divided by R2. The lower trigger point will be my minus V maximum, R3 divided by R2. All right. And then the frequency of that oscillator. The frequency is determined by 1 upon 4R1 times C times R2 divided by R3. That is for my resonant frequencies. All right. Any questions? Any questions? All right, there's an example. Let's quickly have a look at the example. Example 16.4, determine the frequency of oscillation for the circuit in figure 16.3. To what value must R1 be changed to make the frequency 20 kilohertz? All right, we work out the frequency as it is, as the design is, and we get a value of 8,25 kilohertz. Now they say to make F 20 kilohertz, then we must calculate the value of R1, and then we get a value of R1 4,13 kilo ohms. Then my frequency will be 20 kilohertz. All right. All right, here we're going to look at the sawtooth voltage controlled oscillator, a VCO. Voltage controlled oscillators because what are we going to do? We're going to vary this voltage. By varying that voltage, I can control my sawtooth output. All right, I can vary the frequency. All right. Now, first of all, what must we know? Do everybody in this class know the operation of a putt? And what is a putt? Electronics 2. Oh, we go back to electronics 2. What is a PUT? Anybody? All right, it's a programmable unijunction transistor. All right. How does the PUT operate? Do you know that?
Is it the same as the diode?
No, it is not the same as a diode. Let's go a little bit backwards to chapter 11. All right, that's why you must know your electronics to work. Here's the programmable unijunction transistor, the PUT. Now, we look at the PUT, how it's constructed. It's also a 4-layer device. Got an anode and a cathode. All right. Now, if I apply a certain voltage on my gate, all right, let's say I apply 5 voltage on the gate, all right, and this is a negative voltage. Now, to what value must my anode voltage increase before that PUT will go into conduction? I repeat, I got 5 volts on the gate, positive, all right. Now I'm asking, to what value must my anode voltage increase before this device will go into conduction? To what value? All right. It must increase to 0.7 volts higher than my gate voltage. That means if that voltage increased to 5,7 volts, then I will forward bias this PN junction. And when I forward bias this PN junction, the device will go into conduction. You with me? That's why it's programmable. If I vary the gate voltage, I can vary the position where that thing will go into conduction. That's why they call it a programmable unijunction transistor. All right. If I increase that, my anode voltage must increase before before the PUT goes into conduction. And there's the symbol. Now, why must I tell you that? Because we're going to use the PUT in that circuit. All right. Is there any questions? All right, let's have a look at this circuit. I got an input voltage. This input voltage will give me a certain current, because if I got a negative input voltage, this integrator will do what? Will integrate positive, all right? That's why it's negative. That means it will charge a capacitor positive, negative with a constant current, all right? Now, let's assume I got a certain voltage there on the gate of the PUT. Now, the PUT anode voltage must increase 0.7 volts higher than that VP, all right? When I reach 0.7 volts higher than VP, what will happen? The PUT will go into conduction. You see here the PUT is off. It's not in conduction. When I reach that value, the peak value, all right? When I reach that, what will happen? The PUT will go into conduction and will basically discharge the capacitor. You see, discharging the capacitor. And then the PUT will turn off and the whole process will repeat itself. You with me? Very simple. An integrator with a PUT in the feedback loop. All right. The PUT is only there to basically discharge the capacitor. I repeat slowly. PUT is off. What happens? I got a negative input here. The integrator will integrate positive because that's a negative voltage. It will charge the capacitor positive, negative. When this voltage increase to around about my peak value, what will happen? The putt will go into conduction and will discharge the capacitor. Turn off and then it will start charging again. Any questions? All right, here they give us a few formulas for that, for the period and for my frequency. We know frequency is 1 upon the period. And let's have a look at the example. Example 16.5, find the amplitude and frequency of the sawtooth output in figure 16.23. Assume the forward putt voltage is approximately 1 volt. That means when the putt is forward biased and conducting, there's 1 volt between the anode and the cathode. All right, you with me? All right, they say first find the gate voltage in order to establish the approximate voltage at which the putt turns on. All right, what do we got here? We got a voltage divider there at 10K at 10K. That means we want the voltage across R4. That's why it's R4 over R3 plus R4 times 15. It will give me 7.5 volts. All right. That means the voltage on the gate of the putt is 7.5 volts. All right. They say the voltage set the approximate maximum peak value of the sawtooth, neglecting 0.7 volts. That means I can ask you a question where you can basically, I can say don't neglect. If I don't tell you anything, what you will do? You must incorporate the 0.7, all right. In this example, they neglect the 0.7. That means normally that peak value will be 0.7, 7.5 plus 0.7, all right. But now in this case, they say neglected. We're not going to worry about that. The minimum peak value, the low point is, the forward voltage is 1 volt. They say, so the peak-to-peak amplitude, the peak-to-peak is going to be basically 7.5 minus 1, and that will give me 6.5 volts. They say determine the frequency as follows. What is V in going to be? V in is going to be equal to R2 over R1 plus R2 times minus V, and that will give me minus 1,92 volts. I can work out the frequency, and that will give me a frequency of 628 Hertz. Now they say the output waveform is shown in figure 16.33, where the period is determined as follows. If I got the frequency, I can go and determine the period. Period is 1 upon the frequency. Now, the definition of a cycle is from a certain point to exactly the same point. Don't think a cycle is going to be from there to there. A cycle is, there's a starting point, and there's the next starting point, all right? That means that is a cycle, and that is your period, and that's going to be equal to 1.59 milliseconds, all right? My minimum value is 1 volt. My maximum value is 7.5 volts. I will draw it a little bit different. I will draw my 0 there, all right? There you know exactly. There's 0, there's 1, there's 7.5 volts. Any questions? Any questions? No questions? (16.6). The trip 5 timer as an oscillator. Now the trip 5 timer is an integrated circuit. It's quite a useful integrated circuit. You can do a lot of different things with a trip 5 timer. Very useful, not very expensive. You can do a lot of things with a trip 5 timer. System. Sorry, we must first do this. The square wave oscillator. All right, the square wave oscillator. If we look at this circuit, we look at this part of the circuit. What type of circuit is that? What type of circuit is this? It's a differentiator. All right, we got a differentiator, and then we got basically what? What is that going to give us here? Yeah, but what do we normally call that? Yeah, but we call that hysteresis. All right. That means R2 and R3 is going to provide hysteresis. We remember when we did the comparators, we talked about the hysteresis. That means R3 and R2 is going to give me hysteresis. That's going to give me my feedback voltage. All right. And that is going to be a differentiator. All right. All right, what actually will happen here, that is our feedback voltage due to that hysteresis circuit, all right. And I've told you previously what happens normally if that capacitor is completely charged. I will have maximum output. That means the output of that differentiator will go to maximum, all right. When it goes to maximum, I will start charging the capacitor. You can see it's not a linear charging curve because that capacitor is not charged by a constant current, not a linear charging curve. When I charge it, when I start charging positive, the output will be maximum positive, all right? And then when we reach that forward value, then my output will go down negative and I will start discharging the capacitor. Charging, discharging. There's my output. It's a square wave. And that is the positive feedback I will give to the comparator, all right? You see here, there's my feedback voltage, and that's going to be basically positive feedback, all right? And there you can see we are charging the capacitor due to the output of the op amp. Any questions? I repeat, this is for the hysteresis, and that will give me what? Positive feedback. Any questions? All right, now we can go and start looking at the trip 5 timer. Right, that is what we find inside the trip 5 timer. In the trip 5 timer, we got 2 comparators, the upper comparator and the lower comparator. We got a transistor for discharge. We got a flip-flop, and we got an output buffer amplifier there. Now let's go and look at a few things. We look at this resistors, RA, RB, and RC. All of them are 5 kilo ohm resistors. All right, they are equal in value. The flip-flop, how does that work? If I reset a flip-flop, let's first go and look at those things. If I reset a flip-flop, I make my Q output what? I make it a 0. But if you look there, what is that in front of that? It's an inverter. That means it's going to be a 0, and that's going to give me a 1. All right. When I reset. If I set the flip-flop, what do? I make my Q output what? A 1. And there through the inverter, I will get basically a 0. All right. Depending on what the output was, if the output is a 1 and I reset it, then I'm going to make it a 0. All right. I just want you to know what's happening in a flip-flop. Everybody in the class know what happens in a comparator. All right. Now I'm going to put values in here. And then we're going to talk about, first we're going to look at the oscillator, an astable oscillator. When I talk about an astable oscillator, what is an astable oscillator or astable multivibrator? You talk about the bistable, a monostable, and an astable. In digits. In digits, you talk about astable, a bistable, and a monostable. What is astable? What is astable? All right. There they show us something. They say a trip 5-timer connected is an astable multivibrator. See, we put a capacitor there, we put 2 external resistors there, and we put a supply voltage there. All right, there's the IC, and there's the pin connections from pin 1 to pin 8. All right, it's an 8-pin IC. It looks like a 7-for-1 IC. All right. But there's the trip 5-timer as astable. Now, what is the meaning of astable? They tell you it's a multivibrator. That's an oscillator. If it's astable, oscillator is going to oscillate. It's going to give me a square wave or square pulse out. Ooh. What are you doing at this place? I don't know what you're doing here. Don't tell me, sir, we are studying here. Because you're not studying. You don't know nothing about your previous work. No, you don't know anything about your previous work. All right. Let's go and have a look. I'm going to put in values here to make it easy. All right, there's all these 3 resistors are exactly the same value. Let's assume we make the supply voltage here. Let's make it plus 15 volts. You know what's 15 volts? DC, all right. Plus 15 volts there. That means, what will the voltage drop be across all those resistors? There will be 5 volts across each one, all right. That means we look at the first comparator. I'm going to put a value in there. From my reference to that position, there's going to be plus 5 volt. You agree? The next one, what is going to be there? There. You agree? All right. And then we got 15 volts. That's why they talk about a third and they talk about 2/3. At that point, I will have a third of my VCC. At that point, I will have 2/3 of VCC. All right. Now, let's consider a starting point. We're going to start here. We're going to start there. When I start there, we must go and assume the Q output is going to be a 1. All right? That means after the inverter, I will go to give a 0 here. Or low value there. That transistor will be off. All right? The transistor will be off. What will happen? We will start charging. Right, now we can also go and look at the outputs. The output of the voltage across the capacitor here will be low, all right? It will be smaller than that 5 volt. You see there, if this capacitor has not been charged yet, that means it's going to be smaller here. The output here will be, right, if we start charging, go above, positive, I said, all right, yeah. If we go and look at this point here, let's assume the voltage at that point is a little bit higher than 5. Let's say 5,1 volt or 5,01 volt, all right? If I got 5,01 volt, let's say we got here 5,1 volt, for example. There's 5 volts. What will the output be here? Here I got a more positive at my inverting input. The output of this will be a high, all right? Let's say we say it's a 1, all right? It's a high level. What do? I set my flip-flop. If I set my flip-flop, I make my Q output what? A 1. What am I feeding back here? A 0. A 0 there. What can you say about the transistor? It's off, all right? You with me? Now we can also go and look at this one. Here we're also going to have 5,1 volt if we're going to look at that position. It's positive. That's 5.1, that's 10 volts. What is 5.1 with respect to 10? What is 5 with respect to 10? Positive. Huh? It's negative, all right. A negative here. It's negative here. That means what will the output be? It will be negative. Let's say it will be basically a 0 or a low value. All right, you agree? That means the whole story is going to be like that. Now we're going to start charging the capacitor. This capacitor will start charging. It will increase and increase. When it increases to a value just above 10 volts, a tiny bit above 10 volts, what will happen then? Then, you must now remember, that voltage, here it increase, it will make this will become, all right, let me just take this out now. Now let's say I got a positive now, got a positive here of 10,1 volt. That means the voltage there will also become plus 10,1 volt. You agree? All right? Now, if that is 10,1 volt, $10,1 is positive with respect to 10 volt. You agree? All right. The output here will be what? Let's say a high, a 1. All right? This one's output will be what? 10,1 volt is positive with respect to that. What will that be? Close. 10.1 volt will be more positive than that. What will that be? Also 1. No, shouldn't be. Let me have a look. No. All right, there we're going to have 10.1 volts. No, that won't be 10.1 volts. That will be that won't be 10. All right. Here we got now 10.1 volts because we had this position there. All right. You with me? 10.1 volt there. That will give me a high output. And what will happen here? There we had 5.1. Oh yeah. This value here will also change to what? That will now also change to what? 10.1, because if you have a look here, this point will change to plus 10,1 volt. All right. Now, what is 10,1 volt with respect to, what's the voltage going to be here? What's the voltage going to be there? This is going to be plus 5. All right, plus 5 volts. 10,1 volt is positive with respect to 5. That means what will that output be? What will the output be of the bottom comparator? Listen, I got 5 volts there, I got 10,1 volts there. What is 10,1 volts with respect to 5? It's positive, all right. Positive at my inverting input will give me what? All right. You with me? All right, now, what are we going to do? We're going to basically, due to that, we're going to reset the flip-flop. If I reset the flip-flop, what do? I make my Q output what? A 0. I make it a 0. All right. Through the inverter, I make it what? A 1. A 1 here on the base of my transistor. A high state here will do what? Will turn on the transistor. All right? And it will do what? It will discharge the capacitor through R2. All right? That means now we're going to discharge it. We're going to go there. And then we're going to repeat the whole process charging again. All right? You with me? Yes. Any questions? All right, then we can go look further. Again, there is an inverter. That means it's going to invert it, and there's going to be my output. All right. Everybody happy? That's an A-stable, free-running multi-vibrator. All right. All right, here's a few formulas we should know. There's a formula for my resonant frequency. It's equal to 1,44 divided by R1 plus 2R2 times C external. And then they give us the formula for the high state. TH stands for the high state. Is equal to 0,694 bracket R1 plus R2 times C external. That's when it's going to be on the high state. They're going to give us a formula for the low state. There's the formula for the low state, 0,964 times R2 times C external. All right. You can also use that graph here, where you got your capacitance, your external capacitor, and your free running frequency, and then you can go and read it off. Also with those values, you see they say it's R1 plus 2R2. They say the frequency of oscillation, free running frequency of a trip 5 timer A-stable as a function of C external and R1 plus 2R2. The slope lines are values of R1 plus 2R2. That means you can go and read off your frequency or your resistor, your capacitor values there. There they give us for the period. The period is the high state plus the low state, and that's the formula for the period. The duty cycle. Your duty cycle is the high state divided by the period, or the high state divided by the high state plus the low state, because that will give me the period. And you can also use the resistor values to determine your duty cycle. What is the duty cycle? It's basically the high state over my period. How long is going to be the high state compared to my period? All right, now listen to me. They say, to achieve duty cycles of less than 50%, the circuit in figure 16.37 can be modified so that the external charges through R1 and discharges through R2. This is achieved by a diode D1 placed as shown in figure 16.40. The duty cycle can be made less than 90%, and less than 50%. All right, if you want a duty cycle of less than 50%, you must change the circuit to the following. If I want a duty cycle of less than 50%, I must add a diode in parallel with R2. That means charge the capacitor, you're going to charge it through R1 and D, you're going to charge it. When you discharge it, you can only discharge it through R2. All right. That's the difference if you want a duty cycle of less than 50%. All right. All right, there they give us the formulas for that if I want a duty cycle less than 50%. There they give us the frequency and they give us the duty cycle if you do that. Let's have a look at example 16.6. They say a trip 5 timer configured to run in A-stable mode. Oscillator is shown in figure 16.41. Determine the frequency and the output, the frequency of the output and the duty cycle. All right, first of all, they use the formula, determine the frequency, and that's 5.64 kilohertz. The duty cycle, they use the resistor values, and they get a duty cycle of 59.5%. All right, voltage-controlled oscillators. In phase lock loops, they use voltage-controlled oscillators, and we can also use the trip 5 as a voltage-controlled oscillator. They say a trip 5 timer can be set up to operate as a voltage-controlled oscillator by using the same external connections as for A-stable operation, with the exception that the variable control voltage is applied to control input pin 5 as indicated in figure 16.42. As shown in figure 16.43, the control voltage change the threshold values of 1/3 VCC and 2/3 VCC for the internal comparators. With the control voltage, the upper value is V control and the lower value is half the control voltage, as you see by examining the internal diagram of a trip 5 timer. When the control voltage is varied, the output frequency is also varied. All right, there you can see where we put the control voltage in. There's the control voltage. And there's only one thing that's quite important to remember here. They say an increase in the control voltage increase the charging and discharging time of the external capacitor. If I increase the control voltage, it increase the charging and discharging time. Now, if I increase the charging and discharging time, what can I say about my frequency? Will it increase or decrease? It will decrease. Wake up, you're sleeping. If I increase the control voltage, increase the charging and discharging time of the external capacitor and causes the frequency to decrease. All right. If I make the time longer, the frequency is going to be lower. If I make the time shorter, the frequency is going to be higher. All right. And then they say a decrease in control voltage decrease the charging and discharging time of the capacitor and causes the frequency to increase. An interesting application of a voltage controlled oscillator is in phase lock loops, which are used in various types of communication receivers to track various variations in frequency of incoming signals. You will learn about the basic operation of phase lock loop in section 18.8. All right, we don't do section 18.8, but in phase lock loops they use a voltage controlled oscillators. All right. Any questions? All right, that's basically the completion of this chapter.